Tomorrow I will be presenting my senior thesis. So the point of this video is to practice it, see if it fits within a 30-minute time frame. I haven't made the overview slide yet. So I'll figure that out tomorrow. Let me begin with the graphs. So imagine you have 5 people standing in a room with irregularly shaped walls. The blue lines connect the people who can see each other. The red lines connect people who can't. This right here is the graph of the people who can see each other. So if they can see each other in the room, they're connected by an edge. I have, oftentimes you want to label the vertex set so you can construct the adjacency matrix. So the adjacency matrix of a graph is a m by m matrix and is a number of vertices. Vertex I and vertex j, if they're connected, then you label the ij entry of the matrix 1, and then if they're not connected, you label it 0. The adjacency matrix of a graph sort of tells you how the graph operates in a way. So keep in mind the labeling here. If you multiply the adjacency matrix of a graph by a vector with a 1 only at a single position, then the output is going to be a vector with a 1 for every neighbor of the graph. So here, the vector with the 1 only in the 3's position corresponds to the police officer. When you multiply it by the adjacency matrix, you get a vector with 1, 1, 0, 1, 0, which corresponds to the artist, the rock star, and the farmer. So this computation tells you that the police officer could see the artist, rock star, and farmer. One of the most important concepts in analyzing data involving graphs is the graph Fourier transform. So a signal on a graph is a vector and Cn, where n is the number of vertices of the graph. What we do to take the Fourier transform is we compute the eigenvectors of the graph, or of the adjacency matrix of the graph, and then we project the signal onto those eigenspaces. Let me set a timer here. So in graph signal processing, there's this concept of smooth versus non-smooth graph signals. On the left here, we have the cycle graph on 6 vertices. The smoothest signal on the graph is the constant function 1. So you can think of a smooth signal as one which does not change very much from one vertex to its neighbors. On the other hand, on the right, we have the least smooth graph signal. So here, if you start at any vertex and you go to its neighbors, the value of the signal is going to wildly differ. And the graph Fourier transform is able to tell you if signals are smooth. So C6 was the graph we were just looking at. The first signal was the all ones vector, which I'm calling chi0. The second signal was the alternating 1, -1 vector. So these actually happen to be the eigenvectors corresponding to the largest and the smallest eigenvalues of the adjacency matrix of a graph. So the idea is that smooth signals are those whose projection onto the eigenspaces, well, I guess if you project a smooth signal onto the eigenspace of a graph, the largest components will lie along the directions of the eigenvectors corresponding to large positive eigenvalues. There are problems with graph signal processing, however. So in practice, if you're modeling data with a graph, it's always going to change, right? Let's say you are working for Facebook or Instagram or Twitter or something like that. Every time you get a new user, it adds a vertex to the graph, and that actually changes the number of eigenvectors. And as the graph gets larger and larger, it gets more computationally difficult to compute those eigenvectors. So on the right, we have, not my proudest moment, I was computing eigenvectors of a 9,000 vertex graph. And I ended up crashing my computer after using 72 gigabytes of memory. The solution to this, or one solution, involves graph limit theory. So you have a growing sequence of graphs. You're going to find a limit object for that sequence of graphs. But in order to do that, we need a way of comparing the distances between graphs. So here I have two graphs, and I'm going to describe the most basic metric for not the entire space of graphs, but for some graphs. It's based on the adjacency matrices. It's called the cut norm of a matrix. So what you do is you look at well, basically, if you have an n by n matrix, the cut norm of that matrix is you divide by n squared, and then you look at all possible subsets of the row and column indices, and then you're going to sum up the corresponding entries of the matrix. It's easier to see visually. So these are the two adjacency matrices of the graphs we were talking about. This is the difference matrix of those two. So what we're doing is we're maximizing the value of 1 over 25 times sum of dij, where I is in S and T, or J is in T. So I have S in red, I have T in blue. We're going to look at row 1, row 5, column 1, and column 5. Where those rows and columns intersect, we'll have a purple entry in the matrix. We're going to sum those all up. We're going to divide by 25, take the absolute value. So this is the cut we get for these particular subsets of n, but we're going to maximize over all possible subsets. So if we instead take row 2 and row 4, column 2 and column 4, we actually get the same value. However, if we take row 1 and row 2, column 3 and column 4, it's smaller. So this would, we're trying to maximize, so this is not the distance between the two graphs. However, you might notice, as I was saying before, every time a new node is added to the graph, the actual dimensions of the adjacency matrix change. So this metric doesn't work for graphs of different sizes, and we have a solution. We turn graphs into what are known as graphons. So a graphon is a symmetric measurable function. You can just ignore the measurable part. It's sort of difficult to construct a non-measurable function. That's just a mathematical formality. But the symmetric part's important. So that means if you pick x and y, wg of xy is going to be equal to wg of yx. But how you construct this, let's say your graph is on n vertices. You're going to partition the unit interval 0, 1 into n subintervals of length 1 over n. And then you are going to assign the product of the ith interval and the j interval with a value of the ij entry of the matrix. So we're just embedding the matrix into like a higher dimensional space almost. And in this space, we can generalize the cut norm of a matrix to a graphon. And the idea is that if you think about it, as n goes to infinity here, the sums are going to converge to intervals. This 1 over n squared is going to turn into ds dt. And then sup is essentially maximum for infinite sets where the maximum might not exist, but asymptotically there is some maximum value. There are some nuances to be considered, however. I have two graphs displayed above. If we construct their graphons, they don't look close at all. However, we will see that they are actually the same graph. So when we're finding the distance between graphons, we need to consider all possible rearrangements of this unit square. So, for instance, I have a permutation sigma. It's going to send 1 to 2, 2 to 4, 3 is going to stay the same. 4 is gonna go to 1, and 5 is also going to stay the same. I'm going to construct what is called a measure preserving permutation. I call it psi sigma. This is going to send the interval I to I sigma I. Now, what happens when we, instead of looking at a graph on W of x, y, we look at W of psi sigma x, psi sigma y. It actually rearranges the picture. And this looks an awful lot like the graph of the graph that was on the left originally. So the distance between graphs is defined as follows. You embed the graphs, you compute their adjacency matrices, you turn them into graphons, you find the measure preserving permutation, which makes this cut norm value of the difference of the graphons as small as possible, and then that's the distance between the graphs. So here, while these two graphs look far apart, there's a permutation that makes it so when you subtract their graphons, it's 0. And so the key takeaway is that if you have two structurally identical graphs, which we would call isomorphic graphs, their distance is 0. Now this is a very useful idea. And the reason is that sometimes you have a growing sequence of graphs that's going to converge to a graphon and cut distance. And oftentimes, oftentimes in the sense that there's not that many convergent graph sequences. So when you can put them in this framework, it's usually going to give you a simpler object, computationally speaking. For example, there's a random graph model known as the stochastic block model. How it works is you pick block sizes. So we have n numbers, k1 through kn. These are natural numbers, they're whole numbers. And they're going to determine how many vertices are going to go in each block of the graph. We have a symmetric probability matrix. This is a real valued matrix such that if you sum up the entries along any row or column, you're going to get 1. We're going to construct a random graph on a number of vertices equal to the sum of all the block sizes. And then we partition those vertices into blocks B1 through Bn with the corresponding block sizes. And then if I have a vertex U in block I and a vertex V in block J, I'm going to connect them with probability Aij. That's the Ij entry of the probability matrix. So for example, I have a matrix that is valued either 0.2 or 0.8. It's actually easier to see when you look at the graphon. So on the dark squares, the graphon takes the value 0.8. On the light, it takes the value 0.2. This will be the limit object of the sequence of graphs we're going to construct. And so when we actually do construct these graphs, and we increase the number of vertices in each one, so in this case, Gn has 5 times 2 to the n vertices. We get a finer and finer picture that really starts to look an awful lot like this. And that's really because it becomes that graphon. So this is most easily seen when you look at the eigenvalues of these large random graphs. If you divide the eigenvalues, the first 5 largest in magnitude, it actually turns out that all the ones other than the first 5 largest in magnitude are going to converge to 0 when you divide by the number of vertices. But the first 5 are going to converge to the eigenvalues of the graphon, which are slightly different than eigenvalues of a matrix because there's no eigenvectors for a graphon. Instead, you have eigenfunctions because the graphon exists in an infinite dimensional space. However, this graphon, even though it acts, you can turn it into an operator on an infinite dimensional function space. It's only really going to have 5 eigenfunctions that matter. And those eigenfunctions are in one-to-one correspondence with the eigenvectors of the underlying probability matrix. So if I have a stochastic block model graph with 9,000 vertices, instead of computing the eigenvectors and utilizing 72 gigabytes of memory, I could just compute the eigenvectors of the 5 by 5 matrix, which is a lot easier on my computer. use that to approximate the eigenfunctions of the graphon, and then you can use those to approximate the eigenvectors of any large graph in the sequence. Now there is a slight problem with this approach. You might be thinking, why would I even want to work with graphs anymore? Graphons are way better, they're way cooler. However, there really are not that many convergent graph sequences, and the only graph sequences which will actually turn into a graphon are those that have a lot of edges. We call these dense graph sequences. So the rest of this talk and the bulk of my thesis concerns a new class of convergent graph sequences. These are Cayley graph sequences, highly symmetric graphs, and we're going to exploit the symmetries of these graphs to describe a very fitting limit object that is going to be highly related to the underlying groups used to generate these graphs. So Cayley graphs are constructed as follows. You take a group, you take a subset of the group which is inverse closed. The Cayley graph of the group with that generating set, which we call KGS, is going to be a graph whose vertex set is the elements of the group. And if we have two group elements, they're connected, x and y. They're connected if y inverse x is contained in the generating set. So below, I have two presentations of the group of integers mod 8 with respect to different generating sets. So on the left, the generators are -1 and +1. So that means that 0 will be connected to 1, and it will be connected to -1, which in this group is 7. -1 and 7 are the same here. On the right, we use plus and -2 to generate the graph. And so now a vertex is connected to itself +2 and itself -2. So the actual technical details of the Cayley graph convergence, well, they're tough. So before I really dig into it, I want to describe the process by which we associate these graphs with a limit object. So it's based on this framework called action convergence. And the idea is that you take a graph, and this is not the adjacency matrix, but you can think of it as the adjacency matrix. You take a graph, you compute its adjacency matrix, and then you're going to look at the functions defined on the graph, which in this case are vectors. And you want their values to be between -1 and 1. You are going to multiply the matrix by a given vector, and then you're going to treat them both as random variables. So you're looking at the distribution of values of the vector and the matrix times the vector, which induces a probability distribution on R2. The beautiful thing about Cayley graphs is that if you have a large sequence of them, for any distribution that you can construct with a vector and sort of a lower dimensional graph, you will find that exact same distribution. Well, there will be a vector in a higher dimensional space such that when you multiply that vector by the higher dimensional or the adjacency matrix of the higher dimensional graph, you get the same distribution on R2. And as the graph gets larger and larger, so let me actually describe what you're seeing here. The right is just the distribution corresponding to a random vector. The distribution on the left is a particular choice of vector that I'm lifting from the low dimensional space to the high dimensional space to the higher dimensional space and to the highest dimensional space. But it shows how the distributions pop up no matter what. Ugh. That was a really bad way of saying that. Hold on. Let me pause here and try to figure out how I can say this better. So you'll also notice that this distribution has a very nice pattern. And that's because the vector that I chose for distribution is what we would call an eigenvector of the adjacency matrix of this graph. So when you multiply that vector by the matrix, you're going to end up with a stretched version of that vector. And one fact about these distributions is that you know that a vector v is going to be an eigenvector of the adjacency matrix of a graph if and only if the distribution VAV, the joint distribution of V and AV is supported on the line y equals lambda x, where x is, where lambda is the eigenvalue in question. So another interesting fact about these is that I have an eigenvector here that corresponds to a particular distribution supported on the line. I'm lifting the eigenvector into this space in which the adjacency matrix acts. But it's also an eigenvector after being lifted. And it's also an eigenvector of this graph's adjacency matrix. And it's also an eigenvector of this one. So the structure of Cayley graphs, a lot of the important information about them is going to be encoded in the smallest graph, and it's going to be present from the bottom up into infinity, if that makes sense. All right, let me keep playing. Hopefully I'll do that better tomorrow. So the key idea that you need to understand if you want to study sequences of Cayley graphs is the idea of the radon-Nikodym theorem. So if we have a measurable space omega, this little fancy A is called a sigma algebra. And if you don't know what that is, it doesn't really matter. But what measures do is they assign almost a volume or a probability to subsets of some space. So here the space is omega. Unfortunately, not every subset can be assigned a volume. So these are called non-measurable sets. Now in practice, you're almost never going to encounter these, but in math we really always have to take into account even the most niche complexities and formalities. But yeah, let me continue. If we have a measure space. Lambda is the measure on this measure space, so it's the measure assigning volume. And now I'm going to put another measure on this space. We have this idea of absolute continuity. So if for any measurable set in the space, when lambda of S equals 0, so when its volume with respect to lambda is 0, that implies that the measure with respect to nu is also 0, then we say that nu is absolutely continuous with respect to lambda. In this case, there's a unique non-negative function f from omega to the real numbers greater or equal to 0, such that the measure with respect to nu of the set S is the integral over S of f with respect to lambda. So we call f the density of nu with respect to lambda. It's also called the radon-Nikodym derivative, and it's denoted as d nu d lambda. The most important measures in this talk, most groups have, all groups in this talk have, are called R measures. So these are translation invariant uniform measures on groups. What that means is, if I take an element of the group and I take a subset of the group, the measure of that set shifted by x is going to be equal to the measure of the set. And because all the groups in this talk are compact, which, well, there's a lot of different characterizations of that, but you can sort of think about it as they have a finite volume. We can put a probability measure on a compact group. So I'm going to tell you about how I think you should think about Cayley graphs. So if you have a finite group with a trivial topology in sigma algebra, finite groups are really easy. You don't have to worry about any of the non-measurable, weirdness. Everything works really well when things are finite. We have a Haar measure on this finite group. It's a probability measure. And now I'm saying assume you have another probability measure on the group, which is symmetric. By which I mean if we take a subset of the group, then the measure of that subset is going to be equal to the measure of the set containing all of the inverses of the elements inside that subset. The weighted Cayley graph, which I'm going to call K of G nu, is the graph on the vertex set consisting of the group elements, such that the edges x and y, the vertices x and y. Ooh, I need to change that. Let me do that real quick. Such that the vertices x and y are connected with the weight d nu d lambda y inverse x. Now if you want to do a little bit of an exercise, you could show using the above assumptions that d nu d lambda of s is equal to d nu d lambda of s inverse for all subsets of the group. This condition is essentially ensures you have an undirected graph, which we want. Now, what is the significance of this d nu d lambda? So let's say we have a Cayley graph defined with respect to a generating set. So not with respect to a measure. I'm going to show the equivalence of the two definitions. We're going to define a probability measure on the elements of the generating set. So what we do is we sum the Dirac delta function at all the points of the generating set, and then we divide by the number of generators. The Haar measure is the uniform probability measure on the group. The radon-Nikodym derivative of nu with respect to lambda is the number of elements of the group divided by the number of elements of the generating set times the characteristic function of the set. Now suppose you have a complex valued function defined on the group. What happens when you convolve that function with the radon-Nikodym derivative of nu with respect to lambda at a point G? Let's see. Assume you have an element of the group. Convolution of f by d nu d lambda is the integral over the group of f of h, so where h is what, it's like the x when you're doing integral of x dx. F of h times d nu d lambda of h inverse of g. It's actually basically matrix multiplication, and that's the whole point of this example. This is equal to 1 over g, 1 over the number of elements in g, times the sum of the elements of g, of f of h times the characteristic function of s of h inverse g times g over s. What is this? This is saying, oh, h and g are connected in the Cayley graph, right? Because remember, elements are connected if when you multiply one of the inverses by the other, you end up in the generating set. This g cancels out here, so we get 1 over s times the sum of the neighbors of g of f of h. This is just the adjacency matrix times f evaluated at h divided by the degree of the graph. So this measure theoretic framework of the adjacency matrix for Cayley graph is equivalent to the standard, linear algebra definition. So the main idea is that, the normalized adjacency matrix of a simple Cayley graph is going to act by convolving the functions defined on a group with a density of some neighborhood measure with respect to the Haar measure. And my main result basically says that certain sequences of Cayley graphs are convergent, and when they are, the limit object can be described in an identical manner. To put it a little bit more formally, imagine you have a sequence of Cayley graphs. There are certain conditions under which we can find a subgroup of the product of all of the groups in this sequence, and we can find a generating set that's a subset of the product of all the generating sets, which is also going to be a subset of this group. We can put a Haar measure, lambda, on the group, we can put a neighborhood probability measure on this set. And so when these things exist, there are going to be projections from the limit to the graphs in the sequence. And there's going to be, well, when you restrict the projections to the generating set, you get a projection to the generating sets of the graphs, such that if you define a measure by pushing forward this measure lambda on G onto GI, it's going to be the Haar measure. And when you push forward the neighborhood measure onto SI, it's going to be, oh shit, it's my smoke alarm. Okay, in total, we have some notion of a limit of the groups. We have some notion of a limit of the sets, each of which comes with a probability measure that we can project onto all of the groups and generating sets in the sequence in such a way that when we convolve by these projected measures, we're going to end up multiplying by the normalized adjacency matrix. This is the fundamental idea that the rest of this talk is about. So this idea relies on a framework called inverse limits. So if we have a partially ordered set, and what that means is that maybe not all of the elements are like less than or equal to one another, but for any element or for any two elements actually, there's going to be some other element such that both of the original ones are less than it. But if we have a collection of objects indexed by this partially ordered set, and then we have functions called morphisms from the objects in the set to one another. So like whenever I divides j, there needs to be a morphism from the jth object to the ith object. And if I ever divides j and j divides k, then the function that goes from the kth object to the ith object must be equivalent to the composition of the function going from the kth object to the jth object composed with the function going from the jth object to the ith object. So when we have an inverse system of objects in some category, we can develop what we call an inverse limit. So an inverse limit is it's an object that is going to have the structure of all of these objects in the system such that there are projections from the inverse limit to any element in the sequence. And in particular, let's say you project from the inverse limit into the jth object, and then you take the Fij path to the ith object. You must reach the same destination that you would have had you originally started here and just projected into the ith object. Now, the framework for studying graph limits upon which the theory of Cayley graph sequences is based hinges on this idea of a uniform tower. So we have two finite graphs, and we have a homomorphism from the vertex set of the second graph to the vertex set of the first graph. We say that it's AB uniform if the pre-image of any vertex is equal to A. And if we have any vertex in the original vertex set in the domain, and then we have a neighbor of the image of that vertex, then there must be exactly B neighbors of the original vertex which are mapped to that neighbor. And so the nice thing about uniform towers, or I guess a uniform tower, is almost, it's like an inverse limit. It's a sequence of graphs with these homomorphisms, except there's no i's and j's. The homomorphisms only go from I plus 1 to I. That was a terrible explanation. Let's see. You can just think of uniform towers, inverse limits in the category of graphs, with homomorphisms that have a few extra restrictions. So the key result regarding these uniform towers, and this is just the definition of the limit object of a uniform tower, but if you have a sequence of di regular graphs, you construct the inverse limit of the vertex sets using the AB uniform maps as homomorphisms. So now you're going to pick a point in this limiting vertex set, and you want to construct its neighborhood. The way you do this is you're going to construct a new inverse system by projecting x into the ith graph, looking at its neighborhood, doing this for every I, then restricting the AB uniform maps to those neighborhoods, and then taking this inverse limit in the category of sets. When you do this, you get a uniform measure on the neighbors. They're not. The idea of a neighborhood in this infinite setting, it's more of the neighborhood is where this measure is supported. Really, measures, graphs are all about measures. At least when you're looking at like infinite graphs and graph sequences. But yes, you get a uniform measure on this neighborhood. And then there's also a more general uniform measure on the vertex set. And then the limit of the sequence of graphs is going to be an operator on the square integrable functions defined on the limiting vertex set with respect to this measure on the vertex set. But how the limiting operator acts is if you look at AF of x, you're going to integrate over the vertex set of f with respect to this neighborhood measure. So the reason I have these in red is that in a Cayley graph, there's really only one neighborhood, and that's the neighborhood of the identity element. I guess I was already explaining this. I should have gone to this slide more quickly. So let's see, where was I? Okay, I think I'm on point 4. So the limiting operator is defined in terms of these neighborhood measures, but you have to construct these neighborhood measures for every single point in the limiting vertex set, which is kind of annoying and impractical. My claim is, if you have a sequence of Cayley graphs and the underlying groups form an inverse system indexed by n equipped with some partial order, then the neighborhood of x in the limiting vertex set is going to be the shift of the neighborhood of the identity element by x. And this, well, what is the neighborhood of the identity element in a Cayley graph? It's just the generating set. So the neighborhood of a point in the limit is x times the limiting generating set. So I call, or the main idea is that these neighborhood measures they're not really all that distinct from one another. They're all uniquely determined by the uniform measure that you get on the inverse limit of the generating sets. So nu, which I call the neighborhood measure, is really the neighborhood measure of the identity element, but any element can be the identity element if you want to relabel the graphs. So now, just doing a little bit of algebra, if we multiply AF of x using the group structure, we turn nu x into nu of x inverse y, change variables. Now we're integrating f of x, y with respect to nu. We're going to we're going to integrate with, it's like a U substitution. We're going to integrate with respect to a different measure, the Haar measure now, by adding the density function inside the integrand. And we're going to do another change of variables to express this as convolution. So we have f of xy, we're going to do y goes to x inverse y. Now, this is the radon-Nikodym derivative at x inverse y. Now this, remember when I defined this, I said if nu is symmetric, then d nu d lambda of x inverse y is going to be equal to d nu d lambda of y inverse x, and voila, we have f convolved with d nu d lambda at x. Now this is really a beautiful characterization of the limiting object, I think. So to continue recapping, the main idea of Cayley graph convergence is that if we have an inverse system of groups and we have an inverse system of sets that's almost induced by the inverse system of groups, there's a Haar measure on G, it's a probability measure. There's a uniform probability measure, nu, on S, this is the neighborhood measure. If we construct our sequence of graphs, GI is the Cayley graph of Blackboard GI with respect to SI. For any function defined on the group GI, when we multiply the adjacency matrix when we apply the adjacency matrix to the function at a point and divide by the degree of the graph, we are convolving the function with the density of the projection. It's called the push forward, but you can sort of thinking about it as projecting. The push forward of the push forward of nu onto GI with respect to the push forward of lambda onto GI. And the limit of this sequence of graphs, because you can prove that it's a uniform tower, is going to be an operator on the L2 integrable functions of G with respect to lambda. In the same way, when you apply A to a function, you are convolving it with the density of nu with respect to lambda. So A can be thought of as what we call a Cayley graphlon. So this is a symmetric measurable function defined on the pairs of elements in the group. For each pair, you're going to get a number between 0 and 1. Now, unfortunately, I have to actually explain why this works. In dense graph limit theory, we take a graph, we construct the adjacency matrix, and then we construct the graph on. When we study Cayley graphs, the approach is totally different. We take a graph, we do construct the adjacency matrix, but then we're going to look at the vectors or the functions on the vertex set of the graph. Well, I guess these are sort of signals, whose values are between -1 and 1. We treat these functions as random variables. And then we're going to look at the joint distribution of that original random variable and the adjacency matrix applied to it. So this is defined as you divide by the number of vertices, you sum over all the vertices in the graph, and then you look at the Dirac delta function of the vector whose components are v of x and av of x. And then this gives you like almost a collection of points in R2. So the one profile of A is the collection of all such measures where we let V be any function in this set. This is wrong. Yeah, that should be, it shouldn't be the number of elements in V of G, it should just be V of G itself. Why this works. Okay, fix that. So for arbitrary k, you can fix k different vectors that are functions on the vertex set of the graph, and you can look at the simultaneous joint distribution of all k and A applied to all k. Now this one you can't visualize because it's a probability distribution on R2K. So we can only really think about this when K equals 1. But the general idea of the framework of graph limits that we use for Cayley graphs is that a sequence of matrices is going to converge if, well, hold on. Okay. These sets of measures, they actually tell you a lot about AG. However, you need to be able to sort of compute the distance between the K profiles of different operators. So it's not too hard. To compute the distance between the measures, you use this metric called the Levi-Prokoroff metric. And if you are interested in this, you really need to learn about it. Thankfully, to understand Cayley graph convergence, you actually don't really need to compute any distances between graphs, because it's almost as if every graph in the sequence is like sort of fully encoded in the next graph. But when that's not the case, you need to be able to compare the K profiles. So you compare the measures with the Levi-Prokoroff distance, and then you compare the sets of measures with the Hausdorff distance, and then unfortunately you need to compare every single K profile for every value of K at the same time to get the distance between a matrix AGI and AGJ. However, if the sequence converges in that metric, then there is going to be an operator such that when you look at the limit of the closure, so this star refers to the closure of these K profiles, you're going to get the closure of the limiting operator for every natural number K. Now, we have finally arrived to the point where I can explain why the distance metric is not important for Cayley graphs. The general idea is that, let's say you pick some graph in your sequence of Cayley graphs. You pick some function on this graph, and you look at the distribution of the function and the matrix applied to the function. You can find that exact same distribution in the K profile of every single other Cayley graph after it in the sequence, which is really powerful. So in this column, I have the same distribution. Now each of these is corresponding to a different function, but there's a way that you can construct them, which we will get into. And then I just have distributions corresponding to random functions. So you can see that, these distributions are all present. And if you wanted, you could use the function that constructs this distribution and lift it into this K profile. So in a sequence of Cayley graphs, the K profile of a given element is going to be a subset of the K profile of all future elements. Even as the graphs get so large, you can't even really tell what's going on. I mean, that's kind of the idea. Now, we're really going to be relying on measure theory to prove this. And for that reason, we're going to be working with weighted Cayley graphs, because it's the weighted Cayley graphs that converge. Suppose we have two weighted Cayley graphs given by measures nu1 and nu2. And now suppose there's a homomorphism from the second group to the first group, for which the first measure is the push forward of the second measure under the homomorphism. Now, also suppose that if you take any element in G1, when you look at the number of elements of G2 in the pre-image of G, it's going to be equal to the kernel of the function. And so the kernel of a homomorphism is just the elements which get sent to the 0, or the identity element. Now I'm going to pick K functions valued between -1 and 1, defined on G1. Note that when we look at the joint distribution of these functions composed with the homomorphism, which turns them into functions defined on G2, we're actually, well, after some algebra and an application of the first isomorphism theorem, we're going to find that it's equal to the joint distribution of those original k functions. We must also take into account the action of the operator. So what we need to show is that when we apply A2 to the composition of xi and f, it's going to be equal to A1 applied to xi composed with f for all I and k. There's one definition that we'll need. That's the idea of a left shift. So this is the operator on the L2 function space of G1. You define it by L of G of psi of x is psi of G of x. So what it does is if you apply it to a function, it'll multiply the argument by G. Pick any element in G. We're going to look at A2 xi composed with f of G. So this is really just a lot of integrating and changing variables. Let's see. I'd said that the only really important part, I'll just go through it. So we start with the convolution of xi composed with f of h multiplied, let's see. I suppose I could have wrote, remember, this is defined so that when you apply to a vector, what you end up doing is you convolve this vector with the density of nu2 with respect to the Haar measure. We do a change of variables. G goes to, G is a constant. H is going to go to, I skipped a step here. Because this is symmetric, I think what I first do is I turn H inverse G into G inverse H. And then I'm going to send H to GH. This gives us an H argument here, and we have xi composed with f applied to GH. This is a homomorphism, so f of GH is equal to f of G f of H. And then these cancel out, so now we're integrating with respect to lambda 2, or nu2. This is the left shift of f of G applied to xi composed with f of H. Now by definition of the push forward measure, the integral over G2 of xi composed with this homomorphism is equal to the integral over G1 of this function with respect to nu1. And so putting all this together, we have the left-hand side is equal to the integral over G1 of xi f of G h prime. H prime just refers to an element of G1 with respect to nu1. Now we're going to reintroduce d nu1, d lambda 1, or you can always change variables using the radon-Nikodym derivative. That's why it's really nice. And then we are going to rewrite it into a form where it is once again convolution of a function, in this case xi by the density of nu1 with respect to lambda 1. So what we eventually get is that A2 xi composed with f of g is xi convolved with the density of nu1 with respect to lambda 1 applied at the point f of g. But what is this? I guess I didn't say. What did I originally want? Yeah, well that's just this. Let me modify that in my slides. This is A1xi composed with f at the point g. Okay, now that that's fixed. So now we know, I just went up. Okay, you know what, this has probably been confusing. So to recap all this, if we have two weighted Cayley graphs, and we call their adjacency matrices A1 and A2, and we have a homomorphism from G2 to G1, such that the neighborhood measure on G1 is the push forward of nu2 under the homomorphism, and also we must also have that for any G in G1, the number of elements in the preimage of G under F is equal to the kernel of F. This also guarantees that F is surjective. It's very important. That's why we need this condition. Then we know that for any collection of K functions in K functions defined on G1 whose values are between -1 and 1, the joint distribution of those functions composed with F is equal to the joint distribution of those functions. And now we also know that when we apply A2 to the composition xi f, it's going to be equal to A1 applied to xi applied at the point f of g. And so what we then get is that the distribution with respect to A1 of x1 through xk is going to be the same thing as the distribution of x1 composed with f, xk composed with f with respect to A2. And what this means is that because these functions x1 through xk were chosen arbitrarily, every element in the k profile of A1 is going to be contained in the k profile of A2. So to wrap things up, if we have an inverse system of groups and generating sets with limits which are probability spaces G, lambda, and S nu. And I've really kind of been playing fast and loose with the idea of obtaining a probability measure from taking inverse limits, but it would really take too long to discuss the inverse limits of probability spaces. Just know that because all of these spaces are really nice, you end up with a compact limit object, and you can pretty much always put a measure on a compact space, and then the actual topology on that space, which you use to generate the sigma algebra, is going to come from what we call the profinite topology. So you have open sets in all the discrete spaces because every set is open. When you take the preimage under the projection from the inverse limit to the discrete spaces, the preimages of all the sets will be open. And so that gives you a topology. You can use that to construct a sigma algebra. But back to the wrapping up part. We have a sequence of graphs, the Cayley graphs of these GIs with respect to generating sets SIs. The key result, or I guess the key characterization of the adjacency matrix, the normalized adjacency matrix, is that it is convolving functions on the graph, which is the whose vertices are the group. You're convolving functions on the group with the density of the push forward of the limiting neighborhood measure with respect to the push forward of the limiting Haar measure. Now, if I divides j, we know that the projection pi I is equal to the composition of the function going from gj to gi with the projection going from the inverse limit to gj. So remember, what was the condition we had on measures nu1 and nu2 in the prior example, showing the nesting of the profiles? Well, we're going to need nu I to be equal to nu j composed with the, nu I needs to be the push forward of nu j onto gi using this. So by definition, nu I is nu composed with the preimage of the projection function pi I. Pi I is the composition of fij and pi j. When you take the preimage of this composition, you're composing nu with the preimage of pi j with the preimage of fij. But by definition, this is just nu j. And so therefore, we have the relationship we need. And so we can apply what I was just describing to conclude that whenever I divides j, then the k profile of the adjacency matrix of gi, and this is not a weighted Cayley graph, this is a simple Cayley graph, so the edges are valued 0 and 1. It's going to be contained in the k profile of the adjacency matrix of gj divided by the degree of dj. Now, the actual proof of convergence takes a lot more setup, but this is the key idea. I guess the last thing is that the direct limit, because I remember I said earlier, let's see if I can find it. The limit of the k profiles of AI as I goes to infinity is going to be the k-profile of the limiting operator. When you take the limit of nested sets, and this is actually not exact, oh, what the fuck? It's not exactly a limit because the index set doesn't have to be totally ordered, right? It's not just n where, you know, I is always less than j. I'm tripping out right now. It's a more general form of limit called the direct limit. But when you take the direct limit of nested sets, you end up taking all the union of all the sets. And so really the only thing that you would need to do now to show convergence is that you need to prove the union of all of the k-profiles of a gi divided by di is equal to the k-profile of this Cayley graph on, right, whose action is characterized by, well, it's an integral operator. When you apply that integral operator to a function defined on, well, a square integral function with respect to the Haar measure defined on the limiting group, you're convolving it with the density of the neighborhood measure with respect to the Haar measure. If you could take away one thing from this presentation, it is that an undirected Cayley graph of a group is a symmetric measure on the group. And with that being said, I doubt that anybody in the world will watch this far, but if you do, thank you for listening. And then here are the main references. Thank you.